Okay, so it's going to be like this, huh? All right. So last time, well, I should start over since we just started recording. So today we're going to continue talking about section 4.4, which is about graphing sine and cosine functions. Last time we talked about how we can take the unit circle and use that to generate a graph of sine or cosine. And last time we did this, we used angle measures in degrees as our x values, and then the output for sine as our y values. So remember that this is the unit circles in the form cosine theta, sine theta. Today, let's go back and do this now. Instead of using angle measures, though, let's do, angle measures in degrees. Let's do the angle measures in radians, because primarily when we're graphing, that's the measurement, the unit that we use. Goodness gracious, I can't think of anything right now. So typically when we ask you to graph something, we'll be asking you to graph it on from 0 to 2 pi. And I'm just going to do like every pi over 2 units. So like this is pi, this is 2 pi. So here's negative pi and negative 2 pi. So if I wanted to graph the sine function, hopefully yesterday you noticed that when we started putting all these points on there, to get the general like wavy shape that we're looking for, I didn't need to use all of the points to be able to get the picture there, right? So what we're going to do is we're just going to worry about like these 5 points, and that should be enough to get me a good picture of the sine graph. We're going to call these the key points. So for sine, that's 0, 0. That's pi over 2, 1. It's pi and 0. It's 3 pi over 2 and negative 1. And then 2 pi, needs a y-coordinate, 0. So those are the key points. So if I plotted those, I guess I need some tick marks there. Oh my goodness gracious. Help if I put these in the right place. Dang it! I was hoping it wasn't going to take that one too. And oops, that's not where I was supposed to go. That's good. So I have something that looks like this, right? I could extend this now in the reverse direction, just following the same pattern. So like lower, in the middle, upper, in the middle. So it kind of looks like this, right? Is everybody okay with what I did there? To just kind of extend it. So notice that I eliminated like graphing all of this stuff also. I've just narrowed it down to 5 key points that give me an idea of where the peaks or the crests are and where the trough is. Trough. Yeah, this is sine that we graphed. Good question. Thank you. Is that how you spell trough? I don't know. S-P. You think it's got an... Oh, it's got a GH at the end. I'll use spellers. I'm not much of a speller. That's how we're spelling trough? Okay. Sounds good to me. Abigail. So I'm graphing over here, my x value is theta in radians, and my y value is the y coordinate from the unit circle. So I took the radian value 0 and graphed 0, so there's my point 0, 0. And I took pi over 2 and 1, so this is pi over 2 and 1. And then I did pi and 0, and then I did 3 pi over 2 and negative 1. And then I did, well, this is also 2 pi here, right? And then 0 again. Right, so the top of a crest is like a maximum, and the bottom of the trough is like a minimum. And we could do the same thing now for cosine, right? When I graph cosine, I'm going to kind of do the same thing. So this time, to graph cosine, my x-coordinate is still going to be theta, but my y-coordinate now is going to be the x-coordinate in the unit circle. So I have 0 and then 1. I have pi over 2, 0. Pi and negative 1. 3 pi over 2 and 0. And then 2 pi and 1. So there's my graph of cosine. And again, I could extend this in the other direction, just following the same pattern. So now it's going to hit the x-axis, and then we'll have a bottom of a trough, hit the x-axis again, peak of a crest, and I can just kind of match those up. So my key points for cosine are 0, 1, pi over 2, 0, pi negative 1, 3 pi over 2, 0, and then 2 pi positive 1 again. So, again, this guy was cosine theta, is what we just graphed here. Worth talking about features for cosine. So we can talk about the period. The period is like the length of a non-repeating, or the longest non-repeating segment of the graph. So if I start here, this is all different until I get back to here, in which case we start doing the same thing over again, right? So if I look at that, that goes from 0 all the way over to 2 pi. So the period here is 2 pi. The amplitude, that was the distance from a crest or a trough to the midline. So in this case, the midline is the x-axis. It's just the spot that kind of divides the graph into equal halves, so there's the same amount of graph above the midline as there is below the midline. That's 1 unit there. And I guess we could say the mean line, we said, was y equals 0, or the x-axis. So that's all well and good, right? So, okay, so if I just have the unit circle, I can graph sine and cosine by just kind of copying the unit circle down, right? But what if I want to graph something like some transformation of sine or cosine? Well, this is where things will get a little bit more complicated, but not so bad. So I'm going to take a time warp back to your geometry class. And some of you are probably thinking, oh God, geometry. It's not so bad. In your geometry class, you talked about transformations. And there were 4 types of transformations you talked about. You talked about translations. So let's say we have this figure A. You could translate the figure A like left and right. You could translate it kind of up and down, or you could translate it both left and right and up and down, right? So when we talk about a translation, we're just talking about picking the thing up and moving it to a new location. When you're in your geometry class, what we found was if we're doing a horizontal translation, basically to get to my new figure, all I'm going to be doing is changing the x-coordinates, right? So if we're moving it h units over, basically we're just adding h to each of the x-coordinates. If I was, if I was just moving it down, we would just be adding to the y-coordinate. So if I move that k units down, basically I just added k to each y-coordinate. And if I moved it left and right and up and down, well, I would have added to the x-coordinate and to the y-coordinate. We also, in that, another type of transformation were dilations. So you can have 2 types of dilations. You can have one that gets one that stretches it vertically or shrinks it vertically. So you can like stretch it in one direction. So if you're stretching it vertically, the thing that's changing is the y-coordinate. And if you're stretching it by a factor of a, you'd be multiplying each y value by a. You could also dilate in the horizontal direction. If you're moving things horizontally, you're going to be changing your x-coordinates. So if I dilate horizontally, I'd multiply or dilate by a factor of b. I'd multiply the x-coordinates, and then of course we could do both. So I could stretch both vertically and horizontally. And if I do that, I'm multiplying both of the coordinates. The third type of transformation you talked about were reflections. So one type of reflection that you talked about were across the x-axis. So if I'm flipping it across the x-axis like that, the x-coordinates are staying the same, but the y-coordinates are changing their sign, right? And I also talk about flipping them across the y-axis. In this case, the y-coordinates stay the same, but the x-coordinates now are going to change their sign. And we're not going to talk about flipping across both axes when it comes to trigonometry, but that would just be where both coordinates change the sign. And then the fourth type of transformation were rotations. And we don't talk about rotations at all in trigonometry, so we're going to forget about it. So what we want to be able to do is we'd like to be able to graph any translation, reflection, or dilation of y equals sine theta or y equals cosine theta. So, oh sure. Am I going too fast? Okay, well, let me know. We can slow down. We got lots of time. You still have an hour, Megan? It's good that you're not paying attention to the time and you're enjoying what we're doing so much. Abigail. Sure. Okay. Right there? Sure. No problem. Again, if I get going too fast, let me know. And the days where I have to go fast because we have too much to get through, we're recording it also, so you can always double check on the video. If you're watching the video right now, you're probably just like, oh my God, let's hurry up. But that's why I just fast forward. So, haha. Enjoy that, absent people. Okay. So, we're eventually going to put this all together. I promise you these disconnected threads are going to get woven together into something meaningful in a second. We're just kind of taking the long way to get there, but I want to make sure that we both kind of have an idea of where we're pulling or what we're pulling from to generate this procedure we're going to generate here in a moment, and then actually be able to do the procedure. Not that I would ever ask you about any of this like background theoretical stuff on a test or quiz, but I think it helps in kind of understanding what it is that you're doing, that we just go back and revisit some of these things that we've seen in previous classes. So from your Algebra 3 class, we're going to pull from the idea of parent function and family of functions. So we said in Algebra 3-4 that a family of functions is the set of all functions that can be written as a transformation of the, well, let's shouldn't say the A parent function. And a parent function is the, and I'm just going to try not to be so technical, is the simplest form of a class of functions. So why does this matter for us? This week. Daniel Marku. That's for you, sir. I'm guessing it is pants related since it's now October. So you might say, like, why the heck does this matter? Well, why are we talking about this? The set of all sine functions forms a family of functions where y equals sine theta is the parent function. And this set of all sine functions can be represented in the following way. And I guess I'll put a theta there. Yes. The set of all functions that can be written as a transformation of a parent function is a family of functions. So the set of all these sine functions, all these things that we're going to graph, form a family. And the way we can describe that family is in this fashion right here. In fact, it's not even that important, Julia. It's not like something that's super critical. I'm just trying to connect this to ideas that you recognize from previous courses. Is all we're trying to do right now. We haven't gotten anything that's really core to graphing yet. We're just kind of building out. Well, this form actually we're going to use. So that thing highlighted we will use, but like what exactly, like I'm just trying to build kind of a foundation right now. We haven't got into like any example problem or anything yet. Parent function is what I abbreviated that as. So since this is a transformation of y equals sine theta. Was I right?
Yeah.
Yes, I'm smart. What we can say is then, if I start with the parent function, I can take any point on that parent function and transform it into into another function. And I can do so through this map. And this is going to be something, again, that'll be important. We'll use this in a moment. All right. We've we've been like pulling ingredients out of our cabinet here for a minute. You know, it's been more like 30 minutes that we've been doing this. What we're going to do now is we're going to take these ingredients and kind of combine them together and make a procedure that we can use to start graphing sine and cosine functions where we don't use the unit circle directly. Are you guys ready for this? So if you're asked to do something like this, graph 2 sine x, or y equals 2 sine x, from negative 2 pi to positive 2 pi. Of wrong? No, we're going to do this in a second. So this is what we're going, this is an example problem. So we're going to do this right now. We're going to do this graphing problem. So we're going to draw this graph. What I'm going to do is I'm going to begin by writing down the values for A, B, H, and K. And the way I'm going to do that is I'm going to look at this thing here and compare it to this thing here. Is everybody okay with that idea so far? So the A value must be 2. Is everybody okay with how I figured that out? The B value, well, that's the coefficient here, right? What is that number? 1. How did I know that was 1? Because if there's no coefficient written in front of a variable, I can just think of it as 1 or 1 over 1 in this case. Everybody's okay so far? Okay. Now I'm going to look for the H. So the H should be subtracted from the X. So you notice there's nothing there, right? So if I'm not doing any subtracting, that meant that I must have been subtracting 0. And then I'm going to look at the K. What is the K? Yeah, there's nothing there, so I must be adding 0. Correct. Yeah, so Julia asked if there was no coefficient in front of sine. If it was just like sine of yada, 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 that would mean that the A value was 1. Correct. Okay? Now that I have this information, I'm going to now use this. So I can have xy goes to 1 times x plus 0, 2 times y plus 0. Or if I wanted to simplify that down, just x comma 2y. Is everybody okay with that idea? So this xy up over on the left-hand side, these are points in our parent function. These x2y's are going to be points in our transformation. So what I'm going to do now is I'm going to go back and remember what the key points for sine were. So if we go all the way back to the very beginning, we have the key points for sine. I'm just going to copy those now down in the space where we were working. Zoom in, please. Zoom in, please. Too far, please. Thank you. What just happened? Okay, there we go. So I'm just going to copy these key points. And why are we calling these the key points again? When we graphed sine using the unit circle, we decided that this is the minimum amount of information I need to provide to be able to decide where the crests and troughs of that sine wave need to go. And now what I'm going to do is I'm going to use this transformation on each of these key points. So I'm basically just going to plug in the x coordinates and the y coordinates. Is everybody okay with what I'm doing here? So far it's okay. So I'm just kind of plugging and chugging now, right? Is everybody okay with how I generated the points on the left there? So what are these now? These are the key points for the function that I wanted to graph. Oh! So that's it then. I just plot these points and you're done? Almost. Pretty much. Pretty much. Do I need to wait a minute, or is people still copying? I see lots of heads down, pencils moving. I'll wait a minute. I'm not in a rush. I'm not Russian. I'm Polish. I mean, it's close, but... And by close, I mean both Eastern European. Like, obviously, there's a big difference between Poland and Russia. What? I'm a math teacher, not a history teacher. They're both in the Warsaw Pact. I mean, that's saying something, I guess. But it's not the 50s anymore, so I don't know how much that really matters. Okay. So, now that I've generated these key points for my transform function, I can go ahead and plot them. So I have 0, 0, pi over 2, 2, pi 0, 3 pi over 2, negative 2, and 2 pi 0. So my graph will look something like this. Notice, though, that the instructions for this said it wanted me to graph it from negative 2 pi to positive 2 pi. So to finish this off, I need to extend this graph to the left. How am I going to do that? Just kind of follow the same pattern as I have on the other side. So I'm going to have a trough on the midline, a crest, and then on the midline again. And that's not so bad, right? Let's observe something. So notice that the mean line is still at y equals 0, so there's no change there. The period was still 2 pi. So no change there. But the amplitude, that did change, right? The amplitude is now 2. So this tells us something. It tells us that the absolute value of A is going to give us the same thing as the amplitude. So I could figure that out before I graphed it. If I had chosen to and wanted to plot the graph of the parent function the same on the same xy axis, I could also do that. This is just I could do this. Not required to do this, but I'm just doing it to illustrate something here. Oops. So if you're to describe how the red graph is changed from the blue graph, it looks like it has a vertical stretch to it, doesn't it? Like you've grabbed the top of the blue graph and we've pulled up or down on it. Do you guys agree with that? So what that tells me then is that the A coefficient is going to control the vertical stretch, which, if we go back to the translations, and I had a vertical dilation, that was controlled by multiplying the y coordinate. And what does the A value do here? Multiplies the y coordinate. So it should be not a surprise. And in fact, we can predict when we'll have a vertical stretch. And when we'll have a vertical shrink. So notice that I put an absolute value around this, so when the amplitude is bigger than 1, so if that A coefficient is 2, or 1.5, or -6, or -5/4, those are all things where the absolute value is bigger than 1. Each of those will indicate a vertical stretch. If the A value is something like a half, or -3/4, or 0.75, or 0.2, or -0.1, those would all indicate to you a vertical shrink. So the graph would be like squished out, like you sat on it or something. Is everybody okay with that idea? Let's do another. Actually, let's just, for the sake of consistency, let's do that. So let's say we do y equals sine 2x, and we want to graph this on that same -2 pi to +2 pi interval. So how do we start? We want to identify the A, B, H, and K. So for this one, the value for A is 1. The value for B is, this is 1 over B. So this coefficient will actually always be the B value will be the reciprocal of it. So instead of the B value being 2, the B value is 1/2. So just be careful on that. But the B value is always the reciprocal of that number. The H is Anybody? 0. Why is it 0? Yeah. I mean, you could write it like this. And that's still just 2x, right? When I simplify all that nonsense down. And the k value is 0. So now that I have this, what do I do with all this information? I use it to write this map. And again, what is this map? It's bx plus h, and then ay plus k. And once I have this map, I'm going to just take the key points for sine and plug them into my map. So I have 1/2 times 0 plus 0, 1 times 0 plus 0, so that is just 0, 0. Then I have 1/2 times pi over 2 plus 0, and then we have 1 times 1 plus 0, so that is pi over 4, comma 1. And we'll continue doing this. Anybody seeing a pattern going on here with the x coordinates? No? I'll point it out here at the end. If you didn't notice it. Maybe you did and you're just being shy. So if I look at these x coordinates, I go 0, 1/4, 1/2, 3/4, 1. They're all going up by 1/4, right? Okay. Will that always be the case? Well, the x is always going to be going up by the same amount if we're doing it this way. It won't necessarily be 1/4 every time. If we go back to the previous example, they went up by halves every time. I guess I meant 1/4 pi and half pi's. So let's go ahead and draw this. Okay. And so let's go ahead and plot. So I have 1 pi over 4. So if this is pi over 2, that's pi, that's 3 pi over 2, and that's 2 pi. Pi over 4 is going to be like here. And then we're here. Ah! So there's my key points that I've plotted. What do you notice, though? We didn't make it to 2 pi, did we? That's okay. What should we do? Yeah, just continue the pattern. So, do. So let's compare this to the graph of just sine. My amplitude here is 1. Nothing has changed. my period started here and went to here. Whoa. Instead of it being 2 pi, it's just pi. Aha! That's different. And then we have the mean line. Well, that's still y equals 0. That hasn't changed. So what we can conclude is that the b value kind of controls the period, right? And in fact, it does so in this specific way. Oh, the tick marks that I've placed on there? I just usually put 4 tick marks on my graph like that. Usually a half, a pi, 1.5 pies, 2 pies. Yeah, basically just using the key points. Uh-huh. Yes. Sure. Okay. And visually, what has happened here? We've had a horizontal shrink. So we know then that the b value controls the horizontal shrink. When it is bigger than 1, it's going to do a horizontal stretch. And when the b value is less than 1, you'll have a horizontal shrink. Ethan? Yeah. That's okay. Yes. So the vertical stretch is going to be in the y direction, this way. So you notice that still the maximum y values are 1 and -1. So there hasn't been any vertical stretching going on there, right? Does that make sense there? And it's Julie, no. Bella? I wasn't even close. It's a fail. Keep correcting me, and I will, Selena! Yes. You may. Yes. Let's do another example here. So let's say we want to graph y equals cosine of x plus pi over 4 minus 2. We start by identifying A, B, H, K. So the A value is 1. The B value is just 1. Oops, I should probably write it that way. Right? Okay, there. The H value is, negative pi over 4. And now you might be saying, hold up. That doesn't seem right because there's a plus sign in your equation. Why the heck did you write negative for pi over for h? Well, if we scroll back up long ago and we looked at this thing, notice in this general form, what symbol is in there? Minus. So if I plugged in a negative pi over 4 there, minus a negative is positive. So that's why. So you could really think about this as cos 1 times cosine 1 over 1 x minus a negative pi over 4 minus 2. So again, we have A, B, H, and then hopefully nobody has a problem identifying this little guy as our K. What do you guys think? So far, so good? Not too bad. Let's write our map then. So what am I going to write here? B times x plus h, comma, a times y plus k. Everybody's okay here? Okay. Now I'm going to list my key points. One thing I want to point out to you is that we're talking about the cosine function, so the key points are different. So if you go back and looked at the key points for cosine, they are as follows. I'm just going to write them down in the interest of time. Well, whether you're dealing with a sine function or a cosine function, those have different key points, but if you have cosine, you always use the same 5 key points for every cosine, and use the same 5 key points for every sine. But the key points for sine and cosine are different, right? Okay. Just wanted to make sure I was understanding what you were saying. Everybody's good so far? And then what do we do with this? Just plug them in. That's 6 pi, so 5 pi. At the very end, that's a 7 is what that's supposed to be. Is that better? You may. So far, everybody okay? Again, nothing surprising happening here, right? So it's just doing the same thing over and over and over again. This part of the reason why I like doing it this way is that it's literally the hardest thing you have to do is pick out the A, B, H, and K, and then like add, subtract, multiply, divide, and then plot what you get. So it's not too bad, right? Should be a pretty doable procedure there. Now I'm just going to go ahead and graph what we got. So I have negative, oops, I need to do some, make some tick marks here. That's actually maybe smaller than I want. Yeah. Give myself a little bit more space to work with. So my first one was negative pi over 4, negative 1. So this guy is like negative pi over 2. So halfway in there is like negative pi over 4. And then I have positive pi over 4, which is going to be over here, negative 2. You stupid computer. And then I have positive 3/4, negative 3, so that's going to be like there. And then 5/4, that's actually a little, needs to be over a little bit more. That's better. 5/4, negative 2 is like there. And then 7/4, negative 1 is like there. And you notice a couple of things. One is that I don't get all the way to 2 pi, right? So I'm going to go ahead and extend this one more slash, and over here would be my next point. So I'm going to extend to here so that I get past, like 2 pi went to here. So I want to make sure I go at least that far. Everybody's okay with that? You can go further than 2 pi, but we want to make sure we go at least that far. And I'm going to continue my pattern over in this direction. And I'm going to do that same trick over here and extend that one more. And again, really like my graph ends here. That's all I needed to do, but to get that part going over there, I just extended a little bit and went past the end spot. But that's okay. You can do more. Just don't do less. So far, so good here, folks? Okay. So let's look at kind of what's happened here. So let's find that mean line first. If I were to eyeball it, it looks like it's basically this spot right here. You guys agree with that? So this is y equals negative 2. That's changed, hasn't it? Why is it negative 2 now? Well, that's the value for k. Oh! So the k value predicts where the mean line's going to be. You betcha it does. If I look at the amplitudes, or the amplitude, that's still 1, so that didn't change. And if I look at the period, basically we're going from here over to there, which is negative 3 pi over 4, negative 3 pi over 4, to positive, this is negative 1 pi over 4, to positive 3 pi over 4. So again, if I'm going, that's 1 pi over 4, and then 3 pi over 4 more. So that's, this was 7 pi over 4 here. I made a mistake. So pi over 4, 7 pi over 4 more. The period is 2 pi. Helped if I could count. It's the end of the day, guys. The Mountain Dew's wearing off. I had to get another one, and it hasn't helped. My brain is mush. So again, we see the period hasn't changed and the amplitude hasn't changed relative to the graph of cosine, right? But the mean line has. We also might notice that it looks like the graph has been shifted. Typically, the graph for cosine would be here. Oops. As the first spot, and it's been moved down there. Right, so we have two things going on. We have a vertical translation. So if k is greater than 0, we're going to go up by that amount. And if k is less than 0, it's going to go down by that amount. That's what we observe here, right? The whole graph has been shifted down. And we also have a horizontal translation. So when the h is greater than 0, we're going to go right h amount. And when h is less than 0, we can go, left that amount. Yes, Megan? Yeah, we did the mean line. This is it. Right, so the idea is that you have about half of the graph below the mean line and then like half of the graph above the mean line. So that's how I knew where the mean line would be. Or that it's going to be like halfway between the troughs and crests. Is that okay there? We're just kind of using our eyeball to estimate it, but it's usually pretty easy to do. Your eyes are good at picking up those kinds of patterns. Whose brain is pretty much done for the day? Okay, me too. So your homework, we're going to go to the book. So 357, I'd like you to do 1, 3, 7, 8, 11, 23, and then I'd like you to graph this function, this function, and then also graph 61 through 63. So for each of these, I'd like you to graph it from negative 2 pi to positive 2 pi. And make sure when you're doing that, you identify the A, B, H, and K. Right, all of that is graphing. And then find the transformed key points. Which basically means just do the graphing exactly like we had done here, where we show the A, B, H, and K, we draw the map, we show what the new key points are going to be. That's the idea. You may. Yes. All that other stuff too. What's the other stuff? Yeah, so that's a homework problem. Yep. Yeah. So the commas are just separating the homework problems. One second, let me get this.